Um, this is it, the final chapter of the year here, or the season. So in chapter 17, we're going to talk about equilibrium, which I don't know why they do it in this class, to be frankly honest with you, but we'll talk about it, I suppose. So we're going to go through sort of what equilibrium is. When we talk about sort of chemical equilibrium, we're also going to talk about Le Chatelier's principle, which I think is the lab we're going to do today. And then we'll do some calculations that, again, you should not be doing probably in this class until you get to 1B, but we'll talk about how to do those as we do it. So first off, these type of, when we talk about equilibrium and chemical equilibrium, they basically are a result of a certain type of reaction, and these are reversible reactions. So these are the reactions that we've seen before, especially when we talk about weak, say, acids and stuff like that, or weak electrolytes. Where they do go in sort of both directions. So say something like this. And this type of reaction, which has those arrows that do head in both directions, are what are referred to as a reversible reaction. And as we probably have talked about previously, as you go from reactants to product side, sort of in that direction, that is what is referred to as the forward direction in this type of reaction. And at some point, what will happen is you will actually build up enough products, like in this example, C and D, that they will then start combining with themselves and basically head back the other direction. And you will pick up basically the reverse reaction, which is heading from products to reactants, is what is known as the reverse reaction in this case. When we reach chemical equilibrium in a reaction such as this, and as we'll talk about in this chapter, sometimes people have sort of a misconception about what equilibrium basically means. And people go equal, so it's equal amounts on both sides, and that's really not what it means. When we talk about something that has reached chemical equilibrium, what it really means is the rate of the forward direction will equal basically that rate of the reverse direction. So basically, when it does reach chemical equilibrium, as fast as it goes from reactants to products, those products will then recombine and head the other way just as fast. And essentially what that will do is it will lock everybody into place in terms of their concentration, or if you're dealing with pressures, in terms of their pressures, basically where they're at. So, if we started, say, with, 4 molar of this guy and 2 molar of this guy, 0 molar and 0 molar initially. When we reach equilibrium, maybe we got 3 molar and 1 molar and maybe 2 molar and 2 molar on this side, whatever it may be. When that reaction reaches equilibrium, basically what it means is, and my made up numbers there, those concentrations will pretty much remain the same. They really won't change, because as you make some products, you'll make some reactants. So it creates sort of a balance on each side. Again, not in the sense of we have exactly the same amount of everybody on each side, but it creates everybody to sort of lock themselves into place in terms of their concentrations. And they will remain that way until you kind of do something to screw it up, basically. So and that's what Le Chatelier's principle is really about. You can do something that really messes up that equilibrium. But when we do reach chemical equilibrium, what we're really referring to is, again, the rate of the forward direction and the reverse direction basically will equal each other. Any questions on that there? So let's talk a little bit about, refresher, some of the things that we maybe talked about previously, how chemical reactions occur. There is the collision model, which clearly means they need to come in contact with each other. So in order for really reactions to take place, they do have to collide with each other. As we might have talked about previously, maybe when we're talking about energy, they do need to collide with each other, really in sort of the proper orientation and sort of site on each of the molecules. and they also need a certain amount of energy to allow the reaction basically to take place. So the rate depends on the concentration of reactants and products. So when we talk about a rate of the reaction, you know, what that's really the study of is what is referred to as kinetics. And it is sort of how fast or slow a reaction will sort of take place. And for example, here, what has to happen is, for example, these two guys need to collide with each other. As they start colliding with each other, basically, we're going to get some bonds starting to break. And we need to basically break all the bonds that are on the reactive side and obviously form new bonds on the product side. And if you remember, we saw some energy diagrams, I think, that we talked about. And in this case, you know, starting here at the reactant side, we're going to break some bonds as we kind of climb this hill to get to the other side. And we're going to start breaking and making bonds until we get to the top there. And that's what we see here. They collide, they start sort of breaking some bonds, and they also are starting to make some bonds at the process there as well. And again, if you remember sort of our energy diagrams here, that is sort of the process that's occurring as it sort of reaches the top of the hill there in terms of energy. What is this energy? And at the very top of the hill, you do get this sort of complex like we got here, which is, you know, some partially broken bonds, some partially made bonds that are happening. And then relatively quickly, you know, that guy, because it's high in energy, will kind of come down the hill to form our products of this reaction. So remember, sort of a stepwise process where we're breaking all the bonds on the reactant side, making all the bonds on the product side, and we get this sort of intermediate that's in the middle there. It's the highest sort of part of energy, and we'll eventually make our products. The rate does depend on concentration, the reactants, and temperature, and that's two things that does sort of make sense. If we have a very high concentration, that means there is a lot of guys in there, right? Which means they're bound to come in contact with each other a lot quicker than having a very small concentration where there's just a sparse amount of guys kind of floating around in that beaker. It's going to take longer for them to come together and thus longer for the reaction to occur. Increasing the temperature also allows these guys to move around a lot faster. And obviously, if they're moving around faster, there's going to be more collisions. More collisions will lead to more products and probably a faster rate of a particular reaction. Also, by increasing temperature, providing more energy to everybody, which allows them to get up and over sort of the hill to the other side in those things. Obviously, the opposite would be true. If you sort of lowered the temperature, you would then obviously remove a lot of energy from the system. People would be moving around slower. When they do collide, they may not have the right amount of energy for a reaction basically to take place. And you would see sort of a slower rate of a reaction. On average, if you sort of increase the temperature around 10 degrees Celsius for a lot of reactions, you will probably double the rate. So approximately, if you get that temperature up about 10 degrees, it will sort of increase the rate of reaction. Again, for what we've just been talking about, that increased temperature is going to allow everybody to move faster, more collisions, and also people have the right amount of energy in that situation, or more reactants have the right amount of energy really to make products. Any questions on that there? So here's an energy diagram. I think we've looked at energy diagrams before, if I'm not mistaken. And remember, there's sort of two types of energy diagrams that we talked about. And we'll draw this one here, which is our reactants and our products. And when our reactants are higher in energy than our products, this is a exothermic reaction, right? Which means heat and energy is released. And as we talked about, I think in that energy chapter. That means something like our delta H would be negative for this reaction. A negative delta H value means exothermic. And what is happening here, as we talked about, is that hill that everybody has to climb is what is known as the activation energy. And that is the energy barrier that the reactants basically got to climb to get to the other side. And as I mentioned and sort of drew there a second ago, what we are seeing is, again, we're starting to break our bonds and we're starting to make bonds as we kind of come up this hill. When we get to the very top of the hill, that once again is where we have what is referred to as the transition state. And that's where we have sort of that complex that we saw on the previous picture here. That is basically where this guy is housing. This is our guy where we got partially made bonds, partially broken bonds, really that sort of transition guy that's going to occur. Because that is at the peak of energy, as we've talked about, that is going to be very, very unstable. So it doesn't want to be that way because of the partially made bonds and broken bonds. And again, it will come down the hill here to our products. This is exothermic reaction because, again, if you take the difference between where the reactant started and the products ended, that would be our delta H for our reaction, and it actually would be negative in this particular case. That activation energy is the hill that everybody has to climb. So once again, at sort of a normal temperature, there's only a certain proportion of molecules that have enough energy really to get over to the other side. And thus, by increasing the temperature, you're adding more energy to the system, and that will allow a greater proportion to really have enough to climb that hill and get to the other side. Any questions on that there? And obviously, just for a reminder, our endothermic sort of diagram looks a little bit different. Looks something like this. And this would be our endothermic, which means that heat is absorbed. And the delta H here would be a positive number in this particular case. And what we see here is the activation energy here, or that hill that everybody's got to climb, is actually much larger there in an endothermic process. And that's because energy needs to kind of be put in to get our reactants up to our products in terms of energy. So we would expect perhaps this reaction to occur pretty much slower than the first little picture I drew, as it has a much higher activation energy that occurs. And our delta H in this case would be positive, and it is once again the difference between our products and our reactants there, where they start in terms of energy in this particular case. So once again, we do get up to this hill, and it will have our transition state that will kind of fall down. Now, obviously, sort of the larger activation energy, usually it's a little bit of a slower rate. The smaller the activation energy, a little faster in terms of the rate of the reaction. Again, it's just a smaller hill that everybody has to climb. And I think we might have also talked about, one way that you can sort of increase the rate of the reaction, in addition to obviously increasing perhaps the amount of reactants that are there, or increasing the temperature, is you can increase a reaction rate typically by adding a catalyst to the reaction. And a catalyst is not a reactant, it's not a product. It doesn't get used up in the reaction, but is there simply to basically facilitate the reaction happening a lot faster in most cases. There are catalysts that actually slow down, but most people refer to a catalyst as speeding up a reaction. And ultimately, what it's able to do is sort of find an alternative pathway for a reaction to take place. And by doing so, what it does is it lowers the activation energy. So it makes that hill that the reactants have to climb much lower. And the result of that is we do see a speed up in the rate of the reaction. So here is our uncatalyzed reaction. And again, this is the hill that everybody has to climb all the way to the top here. By adding a catalyst here, what it does, again, by finding that alternative pathway, it is able to essentially lower this hill that it has to climb. So obviously, if it is a much lower hill to the other side, that's going to also allow a greater proportion of guys to be able to get up and over. And the result of that, again, is that you would see the rate of the reaction increase. Any questions on that there? And again, you can see here the activation energy hill is much smaller than in the uncatalyzed reaction that we see there. So those are three, sort of common ways that you can sort of speed up a reaction. Again, increase the concentration, increase the temperature, or add a catalyst. Those are three good ways to speed up a reaction. Obviously, if you did each of those the opposite way, it would slow down the reaction. So if you lowered the concentration, the rate of the reaction would go down. If you lowered the temperature, the rate would go down. And then if you did not add a catalyst, obviously it would probably stay where it was, but it would go down a little bit. Any questions on that there? So let us talk then about equilibrium. Equilibrium is the exact balancing really of two processes, one in which the opposite of the other. We do see chemical equilibrium in reactions that are reversible, but we also see equilibrium occur at phase changes. So as we go from solid to liquid, liquid to gas, and so forth, those are equilibrium processes as well. So if you remember sort of our heating and cooling curve, it kind of looks something like this. And if this was water, that was like 0 degrees Celsius. And that would be like 100 degrees Celsius. And this would be like ice. This would be like liquid water. And that would be like steam up here. Now, in a process like this, as we talked about, when we do the transitions here between, say, solid and liquid or liquid and gas, it actually does occur at the same temperature. So 0 degrees Celsius is, again, where we do that transition between solid and liquid for water, and 100 degrees Celsius is where we do it for water between liquid and gas. When you're right at those transitions, it is a flat line here, and you actually do have both phases in equilibrium with each other. So at 0 degrees Celsius for water, you have some ice, you got some liquid water, and they are in equilibrium with each other. And same thing occurs here when we do that transition between liquid and gas, going back and forth. Again, they are in equilibrium with each other at 100 degrees, not until you get above or below those temperatures that we do start to see one phase versus the other. So this process is also always occurring, for example, at the surface of a liquid. So at the surface of a liquid, there's a certain amount of guys that are evaporating and a certain amount of ones that lose enough energy that are dropping back into the liquid. So when we talk about chemical equilibrium, as I mentioned earlier, it is a lot of times involving these reversible reactions where it is ultimately that rate of the forward direction equaling the rate of the reverse direction. And once again, you will basically lock everybody into place in terms of their concentrations or their pressures, and they really won't change because they're basically, again, going back and forth at the same amount. Now, equilibrium is a weird thing in the sense of, frankly, there's an equilibrium constant that is a constant value that you could get as a result of a equilibrium reaction. And it doesn't matter sort of, what you start with. You can start with a little bit of reactants, a little bit of products, no products, all reactants, all products. But it will come to rest at equilibrium with really the same proportion of products over reactants ratio, no matter sort of what you start with. So we'll always sort of come to rest at sort of the same equilibrium. Now, equilibrium is a dynamic process. If you look at a reaction and you did one of these reversible reactions, you may look at this beaker and go, not much is happening at this point. The reaction is over. And if you look at it, maybe it turns red and it stays red, and nothing else really appears to be changing. But there is a lot of activity that is actually happening in an equilibrium process. You have your reactants going to products, you got your products going to reactants. So if you super zoom in on the molecular level of what's going on, there is a lot of activity that is happening to maintain that big picture of it just looks red and nothing much is happening. But there's a lot of activity that's consistently happening in that reaction, going from reactants to products and backwards, to maintain, again, that sort of red color that maybe you would see and you would not look like much is changing. So sometimes it's hard to sort of visualize a equilibrium reaction because, again, it appears to you on the big picture, it's done, nothing else is happening, it's over. But because it is a reversible reaction, this process of forward and reverse directions are consistently happening on the molecular level. And this is sort of what we see, a reaction of H2 and CO to form CO2 and H2. And again, you can see that our count here of our reactants when we start with is pretty much all reactants, no products. And as the reaction goes and continues, at some point it will lock into equilibrium, where in this case we do have a little bit of reactants and products happening. And it will be able to basically continue to maintain those concentrations over a period of time, as long as, again, you don't do anything to disrupt the equilibrium. It will basically lock everybody into place there at the end with the respected concentrations. When we do see a reversible reaction like this, pretty much at the very beginning, if you're just starting with reactants, it's pretty much all going to be, in this case of the example we just looked at, it's all going to be the reactants in the forward direction. So at the very beginning, the forward direction really sort of predominates, and that's what we see here. We have pretty much all reactants, no products. And in order to make products, we have to use up some of our reactants. So we start to see our reactants decreasing with time. At the same time, we are now going to be able to make some products in this case. And in the case of this, it would be our H2 and CO2 being made. At some point, what's going to happen is we are going to build up enough of the products that the reverse reaction is going to basically start. So that reverse reaction will kick in. So at some point, we make enough of these products that they decide, cool, I'm going to come back now the other way. And it will continue this process basically now going in both directions until those rates of the both directions pretty much equal each other. And on a graph, you could really see that by the leveling out here, or plateauing of the rate of the forward reaction and the reverse reaction here basically become the same. And that is the point right there where it levels out, that it does become or reach chemical equilibrium. And you can see past that point, it will continue to be in chemical equilibrium. Again, as long as you don't do anything to mess it up, it will continue that process. So in most reactions, because you pretty much are starting with your reactants, that will certainly initiate the forward direction. But again, as I mentioned, at some point, products will start to appear over here. And enough products will be built up that the reverse direction there will start to kick off. And you can see it takes a little bit of time to sort of build up enough of the products to start that reversed reaction and really get it to equal the forward reaction in terms of the rate. Any questions on that there? So concentrations reach levels where the rate of the forward reaction equals the rate of the reverse reaction. And again, that is the definition there of chemical equilibrium. So if we look at this reaction here, and we have this guy that has reached equilibrium. So we got this guy that's at equilibrium. And we decide that we want to add more H2O here in this particular case. What is going to happen to all the concentration? So what's going to happen to the concentration of H2O, CO, H2, and CO2? Will they go up? Will they go down? Will there be no change? Take a second there and see what you think. Okay, so let's take a look. So in this case, we have a system that's at equilibrium, which means this reaction is going to the product side and back to the reactant side, the reverse and forward direction equal each other. In this case, we are going to add more of the H2O, which is on the left-hand side. What would then happen to our CO concentration? Would it go up? Would it go down? Would it stay the same? Well, let's talk about what would happen when I add the water to that side. Would that make the forward reaction happen or the reverse reaction? Or neither? The forward direction, right? So we added more water, which means water's of a plenty there, right? So it's not going to take long for water and CO to find each other. And that should kick off really the forward direction here for happening, which means if the forward part of this reaction happens, that means we're going to be making products, right? And the only way to make products is you need to use up your reactants. So the concentration of CO should go down, right? And those two would be needed to make our products. The concentration of H2 should then go up, right? Because we are making products, and the concentration of CO2 should also go up once again, because we're making products in this case. Now, water here is kind of a weird one in a sense. Initially, water in this case will actually go up because you added it, right? So obviously the concentration went up. But once the forward reaction starts, we should then see the water's concentration start to go back down. Yeah, so it's artificially going to go up because you added it, so it spiked. But once it starts reacting with the CO, we should start to see it come down. And what you would actually maybe see in this case is you might actually see the concentration of H2O actually be higher than it started with, just because you artificially added it. So because you kind of bumped it up, it went up. But what will happen as that forward direction happens, it will start to come back down as it reacts with the CO. And again, you might actually end up a little bit higher than what you started with. Any questions on that one there? All right, so let's take a look at the sort of same reaction here, but we decide to add H2 in this case. So same thing, what will happen to all of our concentrations? Will they go up, will they go down, or will there be no change if we added H2 in this particular case? So take a second. Looking at, once again, we have this reaction that's at equilibrium. We decide to mess it up, frankly, by adding some H2. So when I add the H2, will this kick off the forward direction or the reverse direction? It should kick off the reverse direction. Again, we have more products. It's going to cause more collisions, going to force this reaction to head in the reverse direction. That should mean our CO2 concentration should go down, right? As we need it to make our reactants in this case. Since the reverse reaction is kicking off here, we would see an increase in the concentrations of both of those. And once again, for the H2, we'll see a similar fact. It will kind of go up because we added it, but then it should start to kind of come back down as it starts reacting in the reverse direction in this case. Any questions on any of those there? Yeah. It would be hard to tell. It depends on sort of where you started with and how much you added. So, you know, if you didn't add a ton, you might end up a little bit lower than where you started with. But if you added a lot just to make sure everything would kind of go the way you want it to go, you may have added so much that even though it starts reacting and reaches equilibrium, you may actually be a little bit higher than when you started with. So, and then that's just basically a fact of you artificially sort of adding it to it and stuff like that. Yeah. But the overall trend, what you will technically see is it should start coming back down wherever it sort of ended up. But ultimately, you may find yourself actually a little bit higher than what you started with because you added more of it. But it should definitely come up and then come back down a little bit as it starts reacting until once again it reaches equilibrium. Other questions? Okay, so as I mentioned before, when we reach equilibrium, there is an expression that we do use to represent an equilibrium, and it is capital K here. And if you take Chem 1B, your class is brought to you by the letter K. You talk about every K ever known to man that you never wanted to know and do. But ultimately what K is an equilibrium constant, and it is a constant value for a particular reaction at a specific temperature. So at a specific temperature, this value will be constant, or a constant value for any reaction. And the way that you do it is you basically take the concentration of the products, and that's what the little brackets mean, by the way. It means concentration. And usually what that means is molarity, which is our moles per liter is what we're talking about there, over the concentration of your reactants. We also take the coefficients that we find in the balanced equation, and they become the exponents when we do that. So we take the concentration of C to its exponent, basically, that's this coefficient. And when you do that, you will get a constant value for that particular reaction. And this is what I was mentioning earlier. You can do like as many experiments as you want, as long as you keep the temperature the same for all the experiments. And in certain experiments, you may start with all reactants and let it get to equilibrium. Certain experiments, maybe you have some reactants, some products, and you let it get to equilibrium. Maybe you got some products and you just let it get to equilibrium. But no matter where you sort of start or how much you start with, as long as you keep that temperature the same and you do your products over reactants, it will always come to the same number. So the ratio of products to reactants will always end up being the same ratio, regardless of how much you start with. And that's sometimes hard for people to understand for equilibrium. It's like, I started with more of A in this case than I did in the first time. Why do I get the same equilibrium constant? So it will reach equilibrium of that rate of the forward reaction. The reverse reaction will always be the same ratio of products to reactants, as long as you keep that temperature constant. Temperature is the only thing that affects the value of the equilibrium constant. And what I mean by that is if you did this reaction at 25 degrees, you would have a value of K of whatever the number may be. If you changed the temperature to 40 degrees and did the same reaction, you would have a different value of K. But if you did the reaction like 4 times at 40 degrees Celsius, all 4 times, they should all have the same value of K, but the value of K between the higher temperature and lower temperature will be different. So what does K help us decide? Well, K, one of the few things in chemistry that is just a number. So there are no units associated with it in most cases. But it does tell us a couple of important things. First off, if we do have a large value of K, would I have mainly reactants or products if I reached equilibrium if I had a large value of K? Which one should mainly be there if K was large? products, right? Just mathematically, you need a large number divided by a small number gives you a large number. So if you see a value of K given to you and it's a large value, it means that when this thing reaches equilibrium, you mainly have products that are present. Obviously, the opposite would be true if you had a small value of K. You would need more reactants than products to get a small value in this mathematical way. And we would expect more reactants to be there at equilibrium. So we can, by just looking at the value of K, have a pretty good assumption of when this thing reaches equilibrium, what we would expect to be there. What is considered a large value? Well, a large value is the big number of 1. So anything above 1 is considered a large value for K. Anything below 1 is considered a small value for K. And there is various degrees of that. There are equilibrium constant values that are like times 10 to the 56, which is a fairly large number. And there are equilibrium constant values that are like times 10 to the minus 34, which is a very, very small number. So, there are various degrees of large and small. If you had something like times 10 to the 56, that pretty much means even though it's a reversible reaction, it's all going to the product side pretty much. It's almost like a one-way street. But because it still is a reversible reaction, even with an equilibrium constant that large, there would still be some coming back the other way. So there's still a reversible reaction, even if it's super, super small, even with a really large K value. And same thing with a really small K value. It would mean that basically everybody's hanging out there on the reactant side. Not much is happening in the forward direction, but a little bit of it is still going in the forward direction as well. Any questions on that there? So if we look at this equation, if we want to write the equilibrium expression for it, which is what this is referred to as the equilibrium constant expression. Once again, we would take our products over our reactants. So that is how we get to the K that we see there. Our products is the concentration of NH3. And once again, the coefficient there is 2. So that is where the 2 comes from. Divided by the concentration of N2. The coefficient here is 1, which is why we don't put anything here. It's just 1, assumed to be 1. Times the concentration of H2 to the third power, because the coefficient there is 3 in this particular case. Now, we'll see this, I think, in a little bit, but we'll just talk about it since we're talking about this as well. There are a couple of things that we do not include. Include with a C, there we go, in the K expression. And there's really 2 things that, we really don't put in there if they are in an equation. And those 2 things are anything that is a solid or a liquid. So those are the 2 things that we do not put into any equilibrium expression, because frankly, a couple of things about that. If it is a solid, it is pretty much just sitting there on the bottom and not much is happening with it. It's not participating in the reaction. So nothing really changes with it. And if it's a liquid like water, for example, that's in the liquid state, its concentration remains pretty much constant throughout the reaction. So it doesn't really affect too much there. That pretty much means that there are 2 things that we do include, which is one of them we see here. We include anything that in the equation has an aqueous symbol next to it or a gas symbol. Aqueous means like ions that are floating around the solution ready to react, so they're good to go. And obviously gas molecules would be flying around. They are good to go and basically to react and stuff like that. So in this case, all 3 of those things were gases, so they all get included. This is also sometimes referred to as a KC. expression, the C standing for concentration. So we use concentration here. We could write a similar one, which is sometimes referred to as a KP. If you had to take a guess, P would be pressure, since we're dealing with gases. And you would do it the same way. You would take the partial pressure squared of your NH3, which is your products, divided by the partial pressure of the N2 times the partial pressure cubed of the H2. And that's what is sometimes referred to as a Kp value, because obviously if we're dealing with gases, sometimes we are given pressures like atmospheres and stuff like that. So sometimes you can write this type of expression as well. For us, we would just probably generically go with the K, Kc, Kp. We'll see Ksp, which is a different one. And pretty much there are tons of different K values. But even though they have like a different letter on the bottom, they are all basically the same idea. They're all basically products divided by reactants when you look at them. By the way, these values here do not typically equal the same numerical value, because obviously pressures and concentrations would be different sort of values, but they do tell you the exact same thing. If you have a large Kp value, you should mainly have products. And if you have a small Kp, you should mainly have reactants in that particular case. Any questions on that there? So K has always the same given value for the temperature, regardless, as I was talking about, the amounts of reactants or products that you start with. So as long as that temperature remains constant, like I said, you could do the same reaction with various amounts of reactants and products. And if you calculate the equilibrium constant value for it, it will come out the same for all of them, regardless of what you started with in each reaction. The reaction that you see and the K value that you see is again associated with a specific temperature. The equilibrium position is a set of different sort of equilibrium concentrations along the way. All right, so why don't you write the expression for this one here and see. All right, let's take a look. So in this case, we would do our equilibrium expression would be our product. So we would take the concentration of H plus, coefficient there is 1, so we would just leave it like that, times the concentration of our acetate. Also coefficient there is 1 in this case, divided by the concentration of our acetic acid. And once again here, that is obviously a coefficient of 1. So this would be it. We would include everybody here since they're all aqueous. By the way, these are all aqueous. The previous one were all gases. These were sometimes referred to as being homogeneous mixtures or equilibrium, where everybody's in the same phase, kind of like a homogeneous mixture, right? Where everything looks the same throughout. So homogeneous equilibrium is one where everybody's in the same phase, as it is in this case, everybody's in the aqueous phase. If we want to calculate the equilibrium constant actual value and we were given values, we would clearly need the equilibrium concentrations to do that, not the initial concentrations. So obviously, if we wanted to put in our values into here, they would have to be equilibrium values in order to obviously solve for a number if we were given those things. So why don't we try that actually? For the following reaction below there, calculate the actual value of the equilibrium constant, and those are some equilibrium concentrations given to us. Equilibrium expression, so that is going to be the concentration of our products. And again, we do need to square it because of the 2 that is there. We want to then divide it by the N2O4, and again, the coefficient there obviously is 1. At this point, since these are equilibrium concentrations, we can just put them in the correct spot there, 0.06, a little squared action, and a 0.055 there. That is going to get us a 0.065 value for the equilibrium constant. Again, there are no units here, so you don't have to worry about units First off, any questions on calculation there? Is this a large value or a small value of K? This is a small value of K, which means when we reach equilibrium, we should mainly expect to have reactants. Yeah. Any questions on that there? All right, we'll lay it up, I think, right now.